Good afternoon, everyone. Pleasure being here, learning a lot about simulation. It's great to be out of the office. Most of the time, we're just putting our heads into the trances and trying to build the next big technology. So let's start this. I'll try and keep it short, 24, 25 minutes. Let's start with why we're doing what we're doing at Log9. So that sets the context why 400 of us show to the office every day. It's an opportunity to unlock this mind to create something that can fundamentally move this species forward in a very responsible way. And we're all about pioneering responsible energy. I mean, we can always find dirty energy, right? We've been drilling holes, getting the juice out, burning it, and moving around with that. There's a much better way to do that. And that has been the fundamental perspective with which this company came out. It's 2015, spun it out from IT Roorkee, great journey, material science, discovered everything on the way. We were never a battery specialist. We are all wiser in hindsight. But we were very, very good at fundamental science, very, very good at mathematics, very, very good at chemistry. We could understand how to play with molecules, how to create lattice structures, how to coat something onto a metal, how to create something that's two-dimensional, not three-dimensional. So that has been the fundamental basis on which this company came through. How Log9 sits in the context of the globe right now. These are some of the companies that are changing the world at this point in time. This is the new age battery cell technology companies. Somebody's trying to do a solid state, somebody's trying to do a fuel cell, somebody like Log9 is trying to do something that's very, very fast charge, and that's the mix. In my perspective, these are the dozen companies that will change how we look at energy and how we store energy, how we generate energy. In our opinion, we try and dissect. We've dissected this world into three quarters, three halves. One is the conventional lithium-ion battery, and if you look at this, the spider web, it's a pentagon. All 5 points point to some properties. So you have safety, cycle life, power, energy, and cost. And those are some of the 5 factors that drive what a cell can do, what the chemistry is supposed to do. If you look at it from a conventional lithium-ion, the green, the colors are visible. The green is what you have now. The blue is where the current R&D is moving towards. If you look at all the papers you study, you get a sense where things are moving forward. If you look at in the conventional lithium-ion, what's happening is we are all going to create, and this has been driven by what Tesla did, if you look at it primarily. Tesla went out and started to claim that they're going to create a car that's going to run 250 miles, 350 miles, 400 miles. It was always a range context. Similarly, we have Lucid Air that says come out now, and they're going about 700 plus miles. So the world has been biased towards mileage. It seems that the batteries are supposed to give you long range, doesn't it? It seems to be one of the most important things to drive your technology towards. is to increase the amount of energy you can hold in a cell. That's the energy density. When you move a material that can hold a lot of energy, it tends to move away from a property to hold it fast enough or to give it fast enough. That means you gain on energy, but you lose on power. And these are two different things. The energy is how much, if I have an energy, I can climb a mountain. How fast I climb is the power. So conventional lithium ion has been driven by that journey of long range, so that we've all seen lithium ion cells that are carrying around 150, 200, 220, 240 watt per kg. That's the amount of energy. So that's a trend you see. Do you see anybody discuss about power? No. And in that context, the safety is something that you try and build, but you're not chasing it. You chase energy, and you want to make your cells, you try encasing, you try and thermal cool it. You fix the safety through secondary mechanisms, not through the primary chemistry. Solid state, on the other hand, has been quite an interesting case. QuantumScape has done a lot of work in that. If you look at it, solid state can push the energy density very, very fast. You can hold a lot more energy. Super expensive. The material science is a little complicated. Is it ready? Do we have a solid state tomorrow? Can we run a Tata car on it tomorrow? It's going to take some time. It's still in R&D. My competing company valued at, I think, about $3 billion. We met them 2 weeks back. They are 3 years from market right now. That's where the tech is. The third one, which is the high power cell, which is on your right, is where we are. This is the Log9 tech that we've been building. And we've said we're not going to build for energy. I'm going to die left, right? I'm going to walk the journey that others are not. What is not visible? And it always happens, you know, when Sabir Bhatia went to sell Hotmail, email was in front of everybody, but nobody did it because what's obvious is not visible. And it became visible to us that what we need to build is cells and chemistries that can release energy fast, that can absorb energy fast, even if it can't hold energy too much. So that's the high power cells. Scores very high on energy. You can really squeeze on, I mean, it doesn't score that high on energy, but you can squeeze out a lot of power from it. I can charge it very fast. I can discharge it very fast. And when you do that, the material allows you to build safeties that I can cut this cell in the middle, nothing will happen. You get a safety profile that everybody is dreaming for through cooling technologies and all of it. If the cell is stable, you think about stressing away from the cooling tech largely. And then you get to a cycle life. We're going to talk about that and why cycle life is important for a context where we are sitting, which is India. Out of that, we created India's first commercial ready cell line. 50 megawatt hour of cell manufacturing already done. The first company in India, the biggest in Southeast Asia. This is an outcome of that. We call it the TIB cell. And what this cell does, with this technology does, I'll break this down. What is TIB? A lot of people have asked us, what is inside it? What is it that you've done different? How is it's giving, how could you take something, a vehicle that was number 5 in India, within 2.5 months it becomes number 1 in India? What did you do with that battery? We are playing these two games. These are the two chemistries that have the potential to be optimized the way we are optimizing. One is the lithium titanate oxide. So LTO is a very different kind of a chemistry. We don't hear about it. LTO was this very, very expensive tech developed in the US and then went to China for a small time. Toshiba has it. But it has been something that's super expensive to make. It requires nanomaterials to be coated onto a plate. Because of that nanomaterial, there are properties in which you can push ions so fast that the nanomaterial can keep absorbing. A lot of people fundamentally don't understand lithium ion cell at an atomic level, so I'll break it down. Imagine all of us are lithium ion. Each one of you is an ion. This room is a lithium ion cell. The air that you're breathing is the electrolyte, and perhaps the chairs are the separators. It's never like that. Separator is always a film, but imagine it in the context of molecules. That's how you will visualize it. If I make half of you stand on that side, that's one electrode. This is the other electrode. When I'm charging, some of you will leave this chair and suddenly go and hit that wall. That's charging. Every time you'll hit that wall will get degraded. So every time you charge, you degrade the plate. Every time you discharge, some of us go and plug on that side. That's the charging cycle. What you have to do is strengthen the walls. You have to make walls such that every time you charge, the bullet that goes, the ion that gets fired from one corner to the another, actually it gets from the electrolyte into that kinetic energy of that bullet hitting that wall doesn't dissipate as heat. That's why batteries get warm when you charge them. It doesn't cause a small hole damage. It doesn't degrade graphite at a molecular structure. Once you understand fundamentally, once you are able to go inside the cell, look at what's happening, then instead of this wall, what if I create a foam, a nano fuzzy layer, a forest? So every time the every time the ion is going, instead of hitting the wall, it will get slowed down by the forest of the nanomaterials. Now instead of charging that cell at 0.5 C, I can charge it at 10 C. Now I can make a vehicle that can charge faster than a mobile phone, right? I don't have to solve the problem for range because you can charge it every 70 kilometers, 10 minutes, go wherever you want to go. Solve the problem differently. What's come out of it is this fantastic RapidX battery that we've created. It's 9x faster than anything that we know right now, anything that's commercially in the market. I can continuously charge it at 20 C. So, it's not even comparable to what we're doing right now at 1 C. It works very well till 60, 65, 70 degrees, no problem. I don't have to cool it at that time. I can get 40,000 cycles, no more 1,000 cycles. I can operate it between minus 30 to 60 degrees. So that means ready for a country like India. What have we achieved with that? 3,000 of these batteries. It's been just 6 months since we launched it in the market. 3,000 packs already there in the market, already hit 20 million in ARR. 51 global patents surrounding all of this tech. 300 plus chargers, because you need to insta-charge, rapid charge them. Well recognized, picked up all the awards on the way. But today is modeling and simulation. So let's talk about modeling and simulation. Are we just the nerd chemistry guys who do this chemical visioning in the company? No, simulation is the bedrock of everything that we do. Because you have to understand things at fundamental level. I could make you part of the ions and the lithium ion cell right now in this room, but how do I do it at my company? I simulate those conditions. I simulate the cathode material. I simulate the nano coating on top of it. And I start to see if I pump in how much ions when I pump in, what's going to be the opening of the crystal structure. If I use a different crystal lattice, will I open it a lot more? Should I use 3.3 mm? Can I go nanometer in my coating? That's how we were able to kind of understand and figure out the different permutation combinations. So in my opinion, in my perspective, simulation for us at Log9 has 2 layers to it. One is what we do at the cell level, at the material level, and second is everything that you heard so far is once you get it up in a vehicle, how does the vehicle functions around it? So I'd break it down. For us, molecular scaling is literally at the lithium ion state. So we look at an ion, we simulate an ion, and see how that ion will move in a Brownian dynamics. A Brownian dynamics is I spray a perfume here, you smell it at the corner. Something happened, right? How did that perfume move? That's classical Brownian dynamics. Similarly, ions have no other way to move but Brownian dynamics. So you have equations that you can simulate and then figure out how the ion's going to move. First you set that system up, then you go to the second system where you create the artificial materials, what you see at the macroscopic scale. Now we're looking at few mm, or let us little bit more than a nanometer. And we start to see, okay, fine, if I have that kind of a coating, what kind of forest, what kind of titanate structure do I need, what kind of crystal lattice do I need to create? That's a lot of simulation that's been done. Once that gets done, then we are firm believers at Log9, all our products are built around a cylindrical cell. So you wanted to understand, will the same technology work in prismatic? Will the same one will work in pouch? What's the liabilities of it? So you realize how much pressure can we hold in a cylindrical form. So those pressure sensing simulations were done. And then fundamentally, when we assemble the battery, how would that look like? What's going to be the heat channel conduction? Even if I heat it up, if something starts to go really, really hot, how hot it will get? Where do I get the air flows in? A lot of also decisions in terms of how to line up the cells to get the least resistance connected back to the circuitry. the biggest question that's been out there is safety. A lot of people have asked why things are burning up. Fortunately, we were part of the committee from the Government of India to help them guide through the process because we were understanding things at a fundamental level at the cell. This is our understanding. This safety is happening because of these three things, and we have to really decode it down. We have to first understand in terms of whenever an EV goes berserk, can you just simply blame that it was built on a wrong chemistry? I'll give you an example. Ola and Ather are both using the same kind of cells. So you can't blame the chemistry there, right? It's NMC. Once you have chemistry like that, you need to understand how to wrap up the cooling systems around it. So it's not the choice of the chemistry, but the choice of secondary systems, choice of sensing systems on top of it. But yeah, you really need to start with the cell and understand what cells. We've seen some companies developing two-wheelers with pouch cells. So we're very, very scared about it because I know the amount of unstabilization that can go through. So we continuously tell that if you have a high abuse use case, use cylindrical, which can vent. So you have to understand from that. If you have an NMC, you need to have auto cut switches at 30, 40, 50, 60 degrees perhaps. Your choice is between NMC versus an LFP. Once you have an LFP, what can you do with that? So you understand fundamentally at cell. In some of those cases, the cells actually went into thermal runaway. And if you look at it, the fundamental studies we have done internally, I'm going to show you one small video. NMC, the moment we push it beyond 60, 65, the material corrosion happens. The moment it touches 80, there's a thermal runaway that kicks in. A lot of people think the thermal runaway kicks in much later. No, it starts at 80. And from 80 to 250, it took a few minutes. And then from 150 to 470, it was 3 seconds. And then after that, it was just 1 second to reach 700. It's almost like a rocket taking off. It's exothermic reaction leading to another heat. What a lot of people are trying to understand is, why are these catching, Cell is a chemistry box. And to cause fire, what do you need? You need fuel, you need oxygen, and you need heat. So there is a critical heat that gets, the oxygen is trapped into those walls. There's a certain thermal reaction will happen that's going to release the oxygen. Once the oxygen is going to catch fire. NMC has that ability to pull that oxygen out. And that's why NMC catches fire. LFP doesn't. So what will happen in LFP is LFP will run into a thermal runaway, will reach to 150, smoke up, and shut down. So if it's critical application, I'll recommend LFP. It won't catch fire, it'll smoke up, and then you have releasing vents to kind of support through that. That's one part. Second part is, let's say poor choice of cell will always put you in the threat of safety. Even if you got some of the best cells, still, Tesla's caught fire. Some of the best engineers work over there. Not many. So that means there is a design level challenge over there. Which is all about when you put things into your battery pack, do you really understand how each cell is operating? One of the fundamental challenges, and for design engineers who are doing battery work over here, was series versus parallel. The BMS is looking at 10 cells as one unit. It has no perception out of those 10 cells which one is going bad. So it continuously kept charging and discharging a pack of 10 cells, where one cell was going weaker and weaker and weaker. And no two cells are same. Out of those 51 patterns that I talked about, some of our initial patterns were how do you bring a bunch of cells together that have similar characteristics. Our first fundamental simulation work, the company got created onto that piece, is how do you assemble, how do you select from a plethora of cells, a set of cells that can be combined to give you the right performance and you don't have a cell disbalancing happening. So understanding how to connect the cells so that you remove those errors where the BMS can see every cell at a given point in time. And you have complexities. You have small cell form factors. 18650s are these small. A vehicle will have hundreds and thousands of it. How are you going to look at all of them? You need to sense voltage. You need to sense temperature each one of them. Only then you have full visibility. Right now, none of the packs have it. And hence, we are in that risky zone. So at Log9, what we did was, everybody's making 18650. We made a 6600 series. I only have 66 cells. I can monitor each one of them independently. I can control how they're discharging, what's the voltage, what's the temperature. In one of the vendors, in one of the OEMs that has been in the news, the wired sensors were hanging right in the middle, not touching even the cell surface. Fundamental, simple oversights of quality. Fair enough, that's the battery side. But there had been accidents where the battery was recovered intact post-fire. That means the battery was never in the fire. How the battery talks to the rest of the power electronics. The batteries are powerful enough. And if you have an IoT device, you have a telematics that's trying to talk to something, and then suddenly the telematics draws some current, and you don't have the right fuse structure into the entire powertrain, the wiring, the wire harnesses. Do you get standardized wire harness? No. You buy it from some Chinese guy, he says warranty for 1 month. That's the shipping time. So you really don't know whether that wire is going to hold the current, that particular voltage is going to be across it. It is the fire's being caught up because most of the body is plastic, and you have a wire that can just have a short circuit because the IoT device pulled more energy, battery drained, and suddenly you have short circuit, no thermal runaway. And that was also one of the cases. So it's the problem. Once you understand it at this fundamental level, you start to see that if you're building an EV, if you're part of that industry, you have to look at all these variables. But having said that, if you understand it, you can actually make EV very secure. Because once you plug all these holes up, it's a very safe system. This is how Log9 cell looks like in its stress test. So we put things to stress test. It's great to have a cell. I can puncture it, I can drill it, I can throw it, I can put it in 250 degrees. The battery will not cause fire now. The most complex piece that you're trying to control, that's going to keep you safe. And if you take care of the rest of the design engineering processes, why should we ever thought about safety? You build it from grounds up into the materials, you make the room safe, the room doesn't catch fire, the building remains same, the foundation remains same. What do we do now? Great technology, great company, innovation. For us, this is our port of call. One of the challenges we are facing is we are importing cells that were discovered in an economy on an IP platform for a particular temperature condition. So it's good to have that particular NMC that runs at 25 degrees. For Tesla, it works because it needs energy density. It can run it at that state. But can you have the same Panasonic cell and solve a three-wheeler platform here in India? No. That three-wheeler is operating at 40 degrees, carrying 650 kgs of load on an incline of, let's say, 7 degrees. And the guy is trying to fast charge it every 4 hours. So you need to build cell chemistries that are built for that temperature condition, for that fast charge and discharge conditions. Now, because this cell, as I said, can take so much of energy, what started to happen is the moment we solved the problem of cell and that particular piece of technology for India, we saw that that's what is needed for the tropics. Every country that sits in the tropic has the same drive, temperature, and use conditions. We don't live in houses that have big garages. We don't have a Tesla that takes an overnight to charge. We live in an apartment and we park our cars 500 meters from our home. How are we going to electrify the streets? You don't have 7 hours to charge next to a tree. So you need technologies that can charge faster. So with Log9, what we've been able to do is a scooter that gets charged in 10 minutes, a three-wheeler that gets charged between 30 to 40 minutes, depending on how big the pack is. So practically, when the driver is taking a break, when the stuff is getting loaded, when the Amazon delivery is happening, you don't really need to have range. Now you have charge. Second is solving the material and supply innovation challenge. The government of India came back to us and said, you know what, you guys can do it in India. When you're building your cell technology, what's the biggest thing that you have that you're faced with? And they thought it's going to be technology, manpower, capital. They said, I need a square inch of aluminum. Can you get me that? Let's begin with that. We are the second largest producer of aluminum in the world. I don't get a square inch of battery grade aluminum. I've always heard this argument that the reason we didn't do lithium ion is because we don't have lithium. I say, well, you had aluminum, you didn't do anything with that either. It's not about availability of the material. It's about finished expertise in material science to create it to the finished level so that it can create those cells. We don't have that. That's where we need to attack. We don't need to go to Congo and buy cobalt. We need to solve simple things. Electrolyte, separator. Separator is not found in Lithuania. Separator is a paper. It's a polymer. You and I should be able to make it. Why do I buy it at $10,000 for a small inch? Beats us. That's where we need to solve for this country. And most important, you have to create technologies that don't make the world worse than what you found it. If it is not good for the climate, we are not interested. That's simple mantra with which we are building this company. So this particular cell technology is designed that it will survive for 20 years. So this battery is not going to go into the landfill. It's going to go good 10, 20 years depending on the use case. And it's highly recyclable. If I can cut it, I can send it to my recycler, he can open it up. And he can extract things out. It doesn't need sandbagging. So fundamentally looking at science as a solution to tech, building solutions for a sector rather than importing innovation, and then addressing the climate. Once you have the 3 pointers in a triangle, you're looking at your true North Star, which is pioneering responsible energy. Thank you.